everyone, today we are continuing on with activity 10. We're actually going to talk about both lessons 10.2 and 10.3, and it starts today on page 135. Now, ideally, when we are doing this unit in class, we do not have a graphing calculator. So one way we can test for potential zeros of polynomials that are not factorable, like the last lesson, is by using the rational roots theorem, which is going to involve us taking all of the factors of our last term, which we're going to call p each time, taking all of those factors and dividing them by all the factors of the leading coefficient, which is what we're going to call q, simplifying all of those to find, in this case, the 10 potential real zeros for this function. Then, to actually figure out if they are zeros or not, we're going to start plugging them in and checking, do they equal 0? Because if they don't equal 0, that's just a point on our polynomial. And if they do, we know that it is in fact a 0 of our function. So in this case, if -2 is a 0, x plus 2 is a factor. Instead of plugging in, we can also use synthetic division to help us not only find out if something is a 0, but also help us kind of create something that may or may not be factorable. So for instance, if we test out -1, one of our potential zeros here, what we see here is when we complete the synthetic division, the remainder is not 0. What this indicates for us is that -1, 5 is a point on our graph, but it's not a 0 because it didn't equal 0 as a remainder. If it does, however, equal 0 as a remainder, so for instance, when we tried -1/2, we completed the synthetic division there, we got a remainder of 0, which means that -1/2 is a 0, and x plus 1/2 is a factor. The other thing that this tells us is that these are the leading coefficients then of each of the coefficients, including leading coefficient, of our other factor, which is factorable. If we take out a greatest common factor of 2, and we have the other two factors, so now we much quicker we're able to find the remaining 2 zeros without having to type all of them in. Okay, so to practice this, let's look at example B here. And B has two factors we have to look at. We have to look at all the key values, so the factors of 3, and then we have to look at all the factors of 2, which aren't a ton, which is nice. And all of our potential zeros then are all of the factors of P simplified divided by all the factors of Q, right? So if we take 1 divided by 1, that's just 1. So +1 and -1 are potential zeros. 3 divided by 1 is 3, positive or negative. So +3 or -3. And then we also want to do that with the second factor. So 1 divided by 2 is 1/2. So +1/2 or -1/2 could be zeros. And then 3 divided by 2, positive or negative, could be 0. So we have 8 potential options here. Well, then to test if these are zeros, one thing we can do is use the store button on our calculator. So here's the store button. I hit 1, stored as x, and I'm going to hit enter. And then I'm going to type in the equation, 2x to the third, and then minus 3x squared, and then minus 8x, and then minus 3. If I hit enter, it automatically stored 1 in there for me to test it out, and it's not a 0. All right, there's a point at 1, -12, but that's not my 0. Now that I have this typed in, I can hit -1, store that as x. And if we go back in our recall, second enter, and hit this enter again, and test out -1 now, it did work out as a 0. Okay, so we could check that out as having a 0 be -1. Now, another one we could test out, if we test out another one, let's say -1/2, I'm going to store that as x this time. And when I check it out, we get another 0. Okay, so -1/2. And then there's one more remaining potential 0, so let's find that one. Should have tested to find that it is 3. Okay. Try this one on your own to find those potential zeros as well. Check your answer on that. And I did your puzzle. All right, now the next one then has for us testing out using synthetic division. So to start this, again, we need to check out the P's and the Q's, right? We need to check out all of our potential zeros. So positive or negative 1 and 3 are the only factors of 3. And then with 4, we have 1, 2, and 4 are factors, which leaves our potential zeros to be positive or negative 1, half, and 1/4, as well as positive or negative 3 divided by 1, which is just 3, 3 halves, and 3/4. So we got a lot of zeros here. Well, let's start by just testing out good old-fashioned 1, okay? And in order to complete the synthetic division, we're going to take those coefficients, and we are going to write those in then. Bring the first term down, got -4, multiply it by our magical number in the box, add down, multiply by the number in the box, add down, multiply the number in the box, and wow, did we get lucky. We got a remainder of 0, so we know that 1 is going to be a 0. So x equals 1 is going to be one of our zeros, okay, which is nice to find pretty quick. Now, what this also allows us to do is say, okay, x minus 1 then, the factor of x equals 1, is one of our zeros. Now, we also can use this remaining values to be the coefficients of the rest. And again, this is a 3rd degree polynomial, so this is 1 degree less. Now, whether you see it or not, we have a factorable situation here, a type 2 factoring, because what multiplies to be -12 adds to be -11. Well, +12 and -1 multiply to be -12, but add to be -11. So we can set this up to be a factoring by grouping situation where we have 2 different factors here. These have a -4x in common, so we'll put x minus 3. These have just basically -1 in common, so we have x minus 3, those still. So our factors, again, don't forget about this x minus 1 that we knew about before, but we're also going to have -4x minus 1 and x minus 3 as our other factors. Now we can set each of these remaining factors equal to 0 to find the other two. So 3 and 1/4 are our 2 remaining zeros, right? And that's a lot nicer than, -1/4. There. Oops. So that we have our 3 zeros to test, or that we don't have to test for, but we put back in and see that they also work. Okay, when in doubt. All right, some nice things about this, all right, is, again, without a graphing calculator, we were able to find these zeros quickly, all right? But one of the drawbacks to the rational root theorem is that sometimes it can be a little time consuming to figure out where are my zeros, and obviously you still will have to worry about complex zeros down the line. So that's where 10-3 comes in. So if we kind of jump ahead a little bit and you look at page 138, okay, we have here the talking about Descartes' rule of sign. And what Descartes' rule of sign does is it kind of limits for us the number of positive possible real zeros versus the number of negative real zeros. Now, we know that these guys are going to decrease each time by an even number, aka you're subtracting 2 each time, because we always think of the pairs that complex numbers come in. Okay, so that's why you're always going to subtract by 2, which doesn't probably make sense first, but we'll look at this. So here's our original function here. And we're going to look for the number of sign changes from positive to negative. Well, here we sign changed 1 time, and then every coefficient was negative. So what this means is there is 1 potential positive real zero, okay? Now, the reason this is nice information is because if we're trying to test out all of these potential P's and Q's, if I found 1 positive number that worked, I can be done testing out the rest of these, okay, if that's what the answer shows here, that it's only supposed to have 1. that's a nice way to kind of know you're done testing things out. To figure out the number of negative zeros that are possible, real zeros, you would plug in negative x for each of the x values in the original, and then simplify, because anything raised to an odd power, now the sign's going to flip-flop from, in this case, positive to negative. Anything that's an even power, well, any negative number squared or to an even degree is going to stay the same. And then this obviously was to the first power, so it flip-flops as well to be a positive. Now we see this is going to change 2 times, which means there's going to be either 2 or 0 real zeros that are of negative value. So again, if you max out, you find your 2, you don't have to keep testing the rest of the zeros to see if they work out. So jumping ahead a little bit, that's actually, oops, I don't have it on here, but there's a check your understanding question about this and like why this is helpful. I believe it's the number 3 on the check your understanding on the next page. And that's kind of what they're getting at on like why that's helpful, because it allows us to help eliminate some of the things. So to kind of test some of these out then with these rule changes, when we look at the try these A, to figure out how many positive zeros there are, if we look here, we went from positive to negative, from negative to positive, and then we stayed positive. So what we see here is for positive real zeros, we're either going to have 2 zeros, real positive zeros, or 0. Again, you always decrease by 2. If we plug in negative x, then negative x to the third minus 4 negative x squared plus negative x plus 5. Well, this simplifies to be now negative x cubed. This is going to go back to be positive since it's squared, so 4x squared minus x plus 5. Well, now we only have one sign change because negative, 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 positive. So we know for our negative, we're only going to have one possible negative real zero. Okay, only one possible. Right. Well, we try one more of these. Okay, let's look at letter C, just because this is a good one to see the potential one here, because there's a lot going on. We have, if we look here, that these are going to flip-flop 1 time, which means that's going from positive to negative 1 time. So there's only going to be possible 1 positive real zero. Okay, 1 possible positive real zero. Now to test out the negatives, however, we need to plug in g of negative x. Okay, and this time this is going to end up flip-flopping because it'll be negative, but this is positive, or excuse me, even, so that won't flip-flop. This will end up flip-flopping because it's to an odd, and then this won't because it's 60 negative x squared, and then minus the 224 negative x, oh gosh, ran out of room, and then minus 192. So when we simplify again, now this is going to be negative x to the 5th. This will still be positive because it's to an even power, so still 9x to the 4th. This is going to flip-flop, so we end up with negative 16x cubed. The x squared is going to stay positive, so we're still just minus 60x squared. This will flip-flop to be positive 224x minus 192. So we see we have 1, 2, 3, 4 sign changes in this, right? So that means there's a possibility of 4, 2, or 0 negative real zeros possible. Okay. Now, again, all of this is going to lead us to being able to try and figure out without a graphing calculator, all right, what our zeros are, and eventually sketch the graph, which we will work with more in class. Okay. Thanks, everyone.